There's this problem in physics, which to this day I think about all the time. Because when I first encountered it, it blew my mind and I had no idea how or why it worked. Even after several lectures on the topic, my mind still couldn't wrap itself around the problem. This problem is central to what is called gyroscopic precession. And here's a video by MIT showing the demo. Now, the question is usually posed like this. Why doesn't the wheel fall? Seems like an obvious question to ask. But it's precisely because of the way this question is phrased that me and many others struggle to understand this problem. Specifically, the use of the word fall. But I'm getting ahead of myself. To understand this problem, we first need to step back and get our hands around some basic ways physicists visualize. Firstly, there's a simple way we represent things that have direction in physics. Simply enough, with an arrow. Physicists call this arrow a vector, and all it is just a way of visually representing these things with direction. A simple example problem using vectors is, say you have a ball rolling north on the ground at a constant speed. You can represent the ball's velocity, that is, its speed and direction, with a vector, unsurprisingly pointing north. Then, let's say some wind starts to blow from the east and begins to push on the ball. You can represent the force of the wind, again with a vector, pointing east. The reason we're talking about vectors is to visually represent these velocities and forces, which will make more sense later on. Now, here's the key conceptual idea you need to understand everything from this point onwards. When you apply a force on an object, the velocity of that object changes direction over time to match the direction of the force. In the case of our ball, the velocity vector of our ball will just begin to rotate around more and more towards the east, as we would expect. Now that we understand the basic language of vectors, let's add to our vocabulary a little. What we've been able to describe so far are things moving in straight lines. But what we're eventually trying to describe is the movement of things rotating. So how can we represent that? Again with vectors, but differently this time. Just as a side note, it's important to stress that this kind of notation is fundamentally arbitrary. What matters is that we use its rules consistently across all problems. And when we do, it works out to describe what we see. So, hear me out. Take a spinning object. Find the axis that it's rotating around. Then, with your right hand, point and curl your fingers in the direction of the spinning. Your thumb then points in the direction of the vector we would use to describe its rotational velocity. In physics, you call this the right-hand rule, and it's how we visually represent the quote-unquote direction something is spinning in. So, for example, a top spinning anti-clockwise on a table would have a rotational vector pointing straight upwards. We now have the tools needed to tackle our spinning bike wheel problem. Remember at the beginning where I said I despise the use of the word falling when describing this problem? Because in reality, what's going on is, sure, gravity is pulling down on the whole wheel, but due to the rope holding it up, gravity is in fact applying a rotational force, one that we can represent with the rotational vector using the right-hand rule. Now this is all well and good, but we have yet to take into account the fact that before we let the wheel tumble over, we spun it up first, giving it a very large amount of rotational velocity. That we can represent using a vector, using again the right-hand rule. Now, what do we notice about both the rotational velocity vector and the rotational force vector? Well, these vectors are perpendicular, or at right angles to one another. Like the ball rolling problem, if an object has a force applied to it, then its velocity changes to match the direction of the force. This rule applies here, So we would expect the wheel to swivel so that the rotational velocity vector matches the direction of the tumbling force applied to it. But here is where we arrive at the key to why this is such a difficult problem to get an intuitive understanding of. As the wheel swivels to match the tumbling, the direction of that tumbling changes such that it's always at right angles to the rotation of the wheel, so they can never match up with one another. So it's left to seemingly defy gravity and spin until friction slows it down enough for gravity to take over.